Hello everyone, and welcome back to what is going to be our final video covering chapter 19 on the heart. So up until now we have covered basically everything regarding the flow of blood. We understand, of course, that blood flows from high pressure to low pressure areas. We've talked about heart valves. We've talked about the electrical conductance of depolarization throughout the different regions of the heart. So one of the major things that is still left for us to cover here is how does heart contractions coupled with those electrical stimulations produce the pumping action that we need to get blood to flow from place to place. So that is going to lead to a big discussion here on the cardiac cycle. So if you'll recall, back to when we talked about electrical stimulation, we said because of the placement of the SA node and because of everything else that we talked about there, the atria are going to contract first, and that will be followed by the contraction of the ventricles. So both the atria and both the ventricles are going to go through a period of cycles in which they contract and then relax, contract and then relax, contract and then relax. The idea being that a contraction will increase the pressure in that chamber so that it can push it into the next place. A relaxation will lower the pressure so that that chamber can accept blood from the prior location. Every coordinated contraction is called systole, and each relaxation is called diastole. Now, it all sounds very complicated, having 4 sets of chambers that each go through systole, diastole. It makes it sound like there's a lot of different things and a lot of different phases to talk about, but really we can boil it down to just 3. So the first one that you can see here labeled A is what is called complete cardiac diastole, and it is exactly what it sounds like. The entire myocardium of the heart is relaxed all at the same time. The atria are relaxed and the ventricles are relaxed. So during this period of time, if you look at the atria here, because they are relaxed, they're at a relatively low pressure, but in spite of that, they are still a higher pressure than what is out in the vena cava. So even though the atria are relaxed and the ventricles are relaxed, the atria can still receive a good amount of blood from the vena cava. And also during this time, since the ventricles are relaxed, they can also receive blood from the atria because in this case, the pressure in the ventricles is lower than the pressure in the atria. So we actually do a lot or a majority of our ventricular filling during this period of complete cardiac diastole. So really, you don't really need the atria to contract in order to get a lot of blood to fill the ventricles. It's kind of counterintuitive that way. So after complete cardiac diastole has occurred, in which both atria fill up with blood from either the vena cava or the pulmonary veins, and then a lot of that blood that's taken into both the right and the left atria, that also leaks into the left and right ventricles. From there, we move on to atrial systole ventricular diastole. So the ventricles stay relaxed, but the atria contract. So when the atria contract, that pushes a small volume of blood from the atria into the ventricles. Keep in mind, we've already done most of our ventricular filling by this point, so we're adding just a little bit of extra on top of that. So we push blood into the ventricles, but you will recall at this point, because the pressure in the ventricles is relatively low, and certainly it is lower than the pressure in the arteries, those semilunar valves are going to be shut. So when the atria contract, the blood moves from the atria to the ventricles, but does not move any further beyond that. Okay, so once we finish with that, we are going to move from atrial systole ventricular diastole to atrial diastole ventricular systole. So during this final stage, the atria are now relaxed and the ventricles are contracted. The atrial pressure is going to go down as they relax. The ventricular pressure is going to go up as they contract. And this is going to close our AV valves because you will recall from part 2 of this lecture series, the AV valves will be shut in cases in which the ventricle pressure is higher than the atrial pressure. So the whole purpose of ventricular systole is that since the blood cannot go backwards into the atria, it has no recourse except to be pumped out into either the pulmonary arteries or out through the aorta to the systemic circuit. The semilunar valves open because the pressure in the ventricles exceeds the pressure in the atria, so we are able to pump blood out into both the systemic and pulmonary circuits. And then once the ventricles are done relaxing, once they have repolarized and begin to relax again, we move back to complete cardiac diastole, and we start this whole process over again. So do not forget, the atria will contract simultaneously, so that's what we mean by atrial systole there, followed by the ventricles. So when we say the atria contract first, then the ventricles, what we're referring to is that we go from atrial systole, ventricular diastole, atria are contracted, ventricles are relaxed, and then we move on to atria are relaxed, ventricles are contracted. So if you look at this diagram, and this isn't the best diagram in the world, you kind of have to look at this for a little bit for kind of all the information here to kind of sink in, but if you look here at this inner ring, that is showing you atrial systole, which does not last very long, and then atrial diastole, which does last a long time. And then this outer kind of pie chart here shows you the period of ventricular diastole and ventricular systole. So from right here, this cutoff right here at the beginning of ventricular diastole, all the way up to this cutoff here for atrial systole, you'll see that the heart actually spends at least 50% of its time in complete cardiac diastole. So your heart actually spends the majority of its time totally relaxed, not contracted at all, either the atria or the ventricles. So as we have mentioned, we are going to go through periods in which the atria contract and then relax while the ventricles contract to pump blood out into the systemic circuit and into the pulmonary circuit. So as I mentioned, the majority of ventricular filling actually occurs during complete cardiac diastole. So we fill up the ventricles with the majority of the blood they can contain during complete cardiac diastole. During atrial systole, we only add a very small amount of blood on top of what is already there in a process which is sometimes called the atrial kick. So before we move any further along here, we want to share some important terminology here. This is going to be extremely important for our assessment of how the heart is functioning during the cardiac cycle moving forward. The first term is called the stroke volume. The stroke volume refers to the specific volume of blood ejected by the ventricles during one ventricular systole contraction. Usually this is going to be approximately 80 milliliters, and that usually corresponds to about 2/3 or somewhere between 60 and 70% of the total volume of blood held in the ventricles. So what that means is that if your stroke volume is 80 milliliters, that means the ventricle must have held previously about 120 milliliters of blood. So that's something that takes a little getting used to. Basically, if you think of the ventricle as a chamber that holds a certain volume of blood, say 120 milliliters, well, only about 2/3 of that 120 milliliters is actually going to get pumped out into the arteries. The remaining 1/3 will be remaining, obviously. The end diastolic volume, or EDV, refers to the volume of blood left in the ventricle during complete cardiac diastole. So essentially what this means is this is basically the full volume of blood in the ventricle. So we did cover the fact that there is a little bit of extra that comes from atrial systole, but your EDV is approximately, you can kind of consider to be the full volume of blood in the ventricle before it contracts. And then the end systolic volume, or ESV, refers to the volume of blood left in the ventricle following ventricular systole. So this is basically that 1/3, or approximately 40 milliliters, that is left in the ventricle following the delivery of the stroke volume. So based on this terminology, we can derive a very easy and simple equation here. Your stroke volume, the volume of blood ejected by the ventricles during systole, is just the difference between the EDV and the ESV. In a typical kind of common situation, your EDV will be about 120 milliliters and your ESV will be about 40 milliliters, which means your stroke volume is typically about 80 milliliters. Your heart rate, which is germane to what we talked about regarding the electrical stimulation of the heart, your heart rate measures the number of beats per minute. And we said for the average person, your resting heart rate is approximately 60 beats per minute. And the most important assessing feature for cardiac function, the most significant output we can get from that, is called cardiac output. This tells us the volume of blood being pumped by the heart every minute. And to calculate someone's cardiac output, you simply multiply the stroke volume times the heart rate. The stroke volume being the number of milliliters delivered per beat, the heart rate being beats per minute. You multiply those together, you should get milliliters per minute. So that is extremely important and extremely telling for us, because someone's cardiac output literally tells you how much blood are they delivering for every minute of activity, and it's important to assess how well they are actually meeting the nutritional and metabolic needs of all the tissues throughout the body. And then something that, I don't know why this is out of order here, but another thing to consider is something called the ejection fraction. So the ejection fraction is basically that 2/3 figure that I gave you before. Basically the idea that every time your ventricles go through systole, they deliver about 2/3 of whatever blood is there, which is the end diastolic volume. The ejection fraction can change sometimes. So the ejection fraction, like I said, is usually somewhere between 60 and 70%, meaning that whatever volume of blood is in the ventricles at the end of ventricular diastole, whatever your ejection fraction is, that's the percentage that is going to get ejected as a stroke volume. Okay, so this diagram that you're seeing here can be extremely intimidating. This is called a wiggers diagram, and there is a lot of power and a lot of information that can be obtained by looking at one of these. But like I said, it is extremely intimidating. If you want me to walk you through a wiggers diagram, you should check out the separately attached YouTube video in which I kind of walk you through this. In this video, I'm going to do this not necessarily quickly, but I'm not going to pay quite as much attention to little details as I would in that other video. So definitely make sure that you check that out. So the power behind a wiggers diagram is that it allows us to, all in one figure, discuss many different features of the heart changing as we go through one cardiac cycle. So several things that we are keeping track of here simultaneously: pressure, meaning the pressure in either the ventricles, the arteries. The video that I'm going to attach separately is going to also keep track of the pressure in the atria, so that should help you out. So you can see over the course of a cardiac cycle how the pressure in the ventricles changes as we go from diastole to systole and back to diastole. We are keeping track of the volume of blood contained within the ventricles. So you can see we go from approximately 120, which is your EDV. After a delivery of a stroke volume, we go down to about 40, which is your ESV, meaning the difference there is the stroke volume that was delivered. And then after one cardiac cycle, you can see the ventricle fills back up with blood and we're ready to all start again. And then the third thing we're keeping track of here, going back to kind of one of the first things that we talked about in this chapter, heart sounds, which we're using to keep track of when the AV valves and when the semilunar valves close. A fourth thing that we could also layer on here, but not in this figure, is your EKG. We can also discuss an entire cardiac cycle with respect to when certain points on the EKG, whether it's a P wave, a QRS complex, or a T wave, when those things occur with respect to other things. So a wiggers diagram, like I said, it's extremely intimidating, but we're going to do our best to explain everything that is happening here as we go through one cardiac cycle. So I recommend you approach this with some patience, because you are not necessarily going to get this the first time through. You may have to kind of go through this several times. So what I'm going to do here is I'm going to flip back and forth between this slide here that is going to explain the different events that are happening in this slide. You will notice that we have these little bubbles here that have numbers in them, 1, 2, 3, 4, and 5. And on this slide, I'm going to have an explanation corresponding to each one of those numbers. So we will take ourselves through this in a fairly methodical fashion here. So if you look at number 1 here, This dotted line here is meant to show you that on this side, we're at ventricular diastole. So right here in this kind of, I guess, peach-colored region to the left of this dotted line, we're in ventricular diastole. So the ventricles are completely relaxed. So we're just about, when you get over to this more yellow shaded area here, we're just about to enter into ventricular systole. So let's take a look at what is happening here right at number 1. So at number 1, because the ventricles are just starting to contract and therefore the pressure is starting to build in the ventricles, the AV valves are going to close. So if you look down here, right at the point where we go from ventricular diastole to ventricular systole, you see the appearance of the first heart sound. And again, that corresponds to the closing of AV valves, which happens anytime the ventricular pressure exceeds the atrial pressure. So we know that that corresponds to the beginning of systole, because as soon as the ventricles contract, the pressure there is going to exceed the pressure in the atria. So we want to close those heart valves to prevent any backflow of blood. So the AV valves have just closed. So this starts our ventricular systole. So this is going to begin a period called isovolumetric contraction. So there's kind of a lot to unpack there. The word isovolumetric, iso referring to the fact that nothing is changing, volumetric referring to the volume of blood. What that literally means is that anytime we're in a period that is isovolumetric, that means the volume of blood in the ventricle during this time is not going to change. We are not going to increase the volume. We are not going to decrease the volume. We are not taking any more blood from the atria. We are not pumping out any blood into the arteries. So because of this, the implication is that the ventricle is going to contract to build pressure while not taking any blood from the atrium, while also not ejecting any blood into the arteries. The idea here is that the pressure in the ventricles during this very brief period is high enough that we want to keep the AV valves closed so that we don't get any backflow of blood. But the pressure in the ventricles is not quite high enough to push that blood out into the arteries. So the semilunar valves are going to be closed as well. The other very important implication of the word isovolumetric is that it means both sets of heart valves are closed. The AV valves have just closed and the semilunar valves are still closed. Anytime you are talking about a period of isovolumetric something, what that literally means, the first thing you should understand from that is that both sets of heart valves are closed. That means the ventricle, if you consider it, has two exits, one exit that leads into the atrium, another exit that leads into the arteries. Both of the exits are sealed shut, so any blood that is in that ventricle is stuck there. It cannot enter and it cannot leave as long as both sets of heart valves are closed. And that is why this is isovolumetric. So, in between these two dotted lines here, the two dotted lines that are bounding that number 1 there, that is the period of isovolumetric contraction in between those two dotted lines. So you'll notice if you look at the volume graph here, you will notice that the volume does not change. It stays steady at 120. So the whole purpose of this isovolumetric contraction is that we want to raise the pressure very drastically in the ventricle. So you'll notice the biggest pressure increase we get here in the pressure chart happens in between these two dotted lines. That is the whole purpose of isovolumetric contraction. We're not delivering blood, we're not taking blood, we're just trying to raise the pressure in the ventricle so that we can get it higher than the pressure in the arteries. So eventually, as the pressure rises and rises and rises, eventually your ventricular pressure does exceed the pressure in the arteries. And something very specific will happen when that occurs. As the ventricle finishes contracting, the intraventricular pressure, as I said, rises past the pressure in the arteries, and this is going to force open the semilunar valves. Recall our rules that we established in part 2 of this video series regarding when the valves are open and shut. So when the semilunar valves open, this provides an escape route for that highly pressurized blood in the ventricles. So now that blood is going to shoot out into the arteries, and we are going to deliver our stroke volume. So you'll notice here on the right side of this second dotted line, this second vertical dotted line, you'll notice that as soon as the pressure in the ventricles is higher than the pressure in the arteries, the volume in the ventricles goes down. That is because blood is being delivered from the ventricles out into the arteries. What we are doing here, as the ventricles continue to contract and push that blood out, we are delivering our stroke volume, which again is usually about 80 milliliters. So if you go from 120 here during isovolumetric contraction to about 40 down here at the end of systole, that is your stroke volume, which is about 80 milliliters. Okay, so the ventricles will continue contracting to get that full stroke volume out until we get to number 3 right here. We're getting to another pair of vertical dotted lines. Well, that's going to tell us something. So blood continues to be ejected out of the ventricles until the pressure in the ventricles falls back below the pressure in the arteries. So just naturally, as we get that pressurized blood out, the pressure on the remaining blood is going to go down. Once the pressure in the ventricles goes back below the pressure in the arteries, we are going to close the semilunar valves again, because that's the rule. If the pressure in the arteries is higher than the pressure in the ventricles, those valves have to be shut. Otherwise, pressure or blood is going to backflow. That is going to produce our second heart sound that you can see right here, the closing of the semilunar valves. So what we have just described, from the time the AV valves shut to the time the semilunar valves shut, that is one period of ventricular systole. You can always tell when the ventricles are contracting if you are in between the first and second heart sounds. So by the time the semilunar valves shut, that tells you that, again, we're back to a period in which the AV valves are shut and the semilunar valves are shut. So this is going to start another type of isovolumetric period. This time it is called isovolumetric relaxation. So both sets of heart valves are closed. We are not taking any more blood. We are not pumping out any more blood. The purpose of isovolumetric relaxation is to bring the pressure in the ventricles way back down. The purpose of bringing the pressure in the ventricles down is that we understand if we want to pump blood again for our next cardiac cycle, we need to fill the ventricle back up with blood, because 40 milliliters left over is not really going to do it for us. That's not going to be enough to pump out to meet the demands of all our tissues. So we want to get the pressure in the ventricle back down below the pressure in the atria, because that's the only way the ventricles will be able to fill back up with blood, if the pressure in the ventricle is below the pressure in the atria. So during isovolumetric relaxation, we bring the pressure way, way, way down, and once we get to the point where the pressure in the ventricles is back below the pressure in the atria, the AV valves are going to open back up, again, because that is the rule that we established. So when the AV valves open, the ventricles can now fill back up with blood. So this marks the beginning of complete cardiac diastole. And again, most of this filling occurs before that atrial kick, before atrial contraction. And then if we go back to looking at 4 here, you can see we are filling back up with blood. The ventricles are relaxed. The pressure is very low, below the pressure in the atria. So we fill back up with blood to a great extent here. Until we get to number 5 here, you can see we add a little bit of extra blood there. That corresponds to atrial systole. So we're just adding a very small amount of extra blood there as the atria contract. So from number 5 there, you just go back to number 1 at the top here, and you start all over again for your next cardiac cycle, for your next heartbeat. So let's go ahead and sum up a lot of what we've learned here. A couple of very important things that I want to make sure that you take away from this. So in order for blood to be ejected from the ventricles into the arteries, the pressure in the ventricles has to be higher than the pressure in the arteries. That was the most fundamental thing I tried to get you to understand in part 1 of this video series. Blood will always move from high pressure to low pressure. So if we want blood to go from the ventricles to the arteries, we want the pressure in the ventricles to be higher than the pressure in the arteries. But at the beginning of this cardiac cycle, when the ventricles are relaxed, the pressure in the ventricles is way, way, way below the pressure in the arteries. So that is the purpose of isovolumetric contraction. We want to raise that ventricular pressure so that it does get above the arterial pressure, so we can open those semilunar valves, so we can deliver our stroke volume. And then in order for blood to fill the ventricles after a cardiac cycle has occurred, in order for blood to fill the ventricles from the atria, the pressure in the atria has to be above the pressure in the ventricles. So again, that is the whole purpose of isovolumetric relaxation. We want to get the pressure in the ventricles back down below the pressure in the atria so blood can move from the atria to the ventricles. And like I said, the word isovolumetric should tell you one very specific and very important thing. It means both the AV valves and the semilunar valves are closed. So if we go back to this chart here, if you see these two dotted lines, if you're in between those two dotted lines here or here, it means that the heart valves are both closed during those circumstances. So the bottom line here is that the ventricles will go through periods of isovolumetric contraction in order to raise their pressure for ejection, and isovolumetric relaxation to lower their pressure for filling back up. If you understand that much right away, then you're probably in pretty good shape. Okay, so another thing that I mentioned is that the most meaningful feature of cardiovascular function, the most telling thing that we can calculate, is the cardiac output. So cardiac output, as a reminder, is the volume of blood in milliliters or liters pumped per minute. And that is equivalent to the stroke volume, milliliters per beat, multiplied times the heart rate, which is beats per minute. So basically, the cardiac output is just a measure of how much blood is delivered to the systemic circuit per minute. How ably are we going to meet the nutritional and metabolic demands of all of our different tissues in the systemic circuit? So let's plug in some figures here. Let's have kind of a liberal estimate here. Let's say the average heart rate for someone is about 72 beats per minute. Maybe a little high, but let's just go ahead and say that. So what this means is that if someone has a stroke volume of about 70 milliliters per beat, the cardiac output would just be the product of those two numbers, 72 times 70, which would be about 5 liters or 5,000 milliliters per minute. So do you remember about how much blood is contained within the average human body? It's about 5 liters. So what this is telling you is that someone who is just in their resting state, 72 beats per minute, 70 milliliters per beat is their stroke volume, they are circulating their entire blood supply every minute. So that's kind of crazy to think about. But the cardiac output is something that is very fluid. It is something that can be changed in order to meet the demands of our body under a number of different circumstances, and as such, it is influenced by a number of different factors. You are, as kind of a preamble to this discussion, you are aware that if you were to go outside and go for a 5-mile run, your heart rate is going to go up. So that would obviously increase your cardiac output. So there must be something that is telling your heart you need to beat faster to meet the metabolic and nutritional demands of all of your tissues. And we, of course, understand that to be the sympathetic nervous system. So let's talk about the different circumstances in which your cardiac output can change. Specifically, let's talk about the different factors that affect your cardiac output. So let's start at the bottom here. Cardiac output equals your heart rate times your stroke volume. So what we're going to do here is we're going to look at this in two different ways. What sorts of things can change my heart rate? What sorts of things can change my stroke volume? So we'll just have those two discussions, and based on this very simple formula, we have derived CO equals HR times SV. Based on how we understand the heart rate and the stroke volume changing, we can also very easily predict how your cardiac output is going to change. So you can see here your heart rate can be influenced by things like your age, your fitness level. So very well-trained athletes tend to have very low resting heart rates, hormones, But the most important one that we are going to talk about is autonomic innervation. Of course, we have talked about how the parasympathetic division will lower your heart rate and the sympathetic division will raise your heart rate. And that's really all we will talk about with regard to heart rate. Your stroke volume is a much more complicated issue. So your stroke volume will be influenced by things like fitness levels, your gender, the size of your heart. But then the things that we'll be talking about are things like contractility, preload and afterload, mean arterial resistance, the resistance to blood flow in the arteries. So the stroke volume and the factors that affect it are going to be a little bit more complicated. So we'll have those discussions here very shortly. So like I said, you're already aware that the parasympathetic and sympathetic divisions innervate the SA node of the heart and can raise and lower the heart rate respectively. And then epinephrine, we also mentioned, can do the same thing that norepinephrine does. So it is a purveyor of the sympathetic response. And then I also said the stroke volume, the volume of blood delivered by the ventricles per cardiac cycle, it's multifactorial and it can be influenced by a number of different things, including the sympathetic division of the ANS. So let's dive into this. So all the way back in the autonomic nervous system chapter, which was chapter 15, I mentioned that there are autonomic control centers in the medulla, the pons, and in the hypothalamus. And I said we're not really going to focus on this right now. It would be better for us to wait until we get to cardiovascular, until we get to respiratory, until we get to urinary to actually talk about what those things do. Well, here is the time for two of them. There are two cardiovascular control centers within the medulla oblongata. You can see them right here. So, for parasympathetic activity, we're talking about the vagus nerve. So the vagus nerve projects parasympathetic fibers to both the SA node and to the AV node. And any acetylcholine that is released from these postganglionic fibers is going to slow your heart rate down, but we've talked about that. Sympathetic fibers do not go through the vagus nerve, but rather through the spinal nerves that we've talked about before. Remember that? Parasympathetic nerves tend to go through, or parasympathetic pathways tend to go through cranial nerves, sympathetic tend to go through spinal nerves, so don't forget that. So sympathetic fibers project through a spinal nerve to the SA node if we want to speed up the heart rate, or also to the actual ventricular myocardium if we want to increase our stroke volume, which we'll talk about that more later. So let's talk first about the autonomic control of our heart rate. So don't forget, parasympathetic activity, innervation on the SA node will slow your heart rate down. Sympathetic activity will speed it up. So what we want to understand here is we want to go back to what we know about pacemaker potential. So don't forget our discussion that we had in part 2.2 of this lecture series on chapter 19 regarding pacemaker potential. So if you get lost here, you may want to go back and look at that again. Okay, so what you're looking at here on top here in this top figure is what your normal resting heart rate looks like, right? So you have a slow depolarization coming from those funny sodium channels, a very fast depolarization coming from those voltage-gated calcium channels, and then a very quick repolarization from the voltage-gated potassium channels. So that ensures that you get a pacemaker potential every second or so, right? So those funny sodium channels ensure that you will always depolarize until you get to a certain threshold, so an action potential is always going to happen one right after another. So let's look at what sympathetic and parasympathetic activity do to change this. So let's start with sympathetic. So sympathetic activity can either come from epinephrine in the blood or norepinephrine coming from postganglionic neurons. So when these two, whether it's the hormone epinephrine or the neurotransmitter norepinephrine, when they bind to beta-1 adrenergic receptors on the SA node, this is going to open ligand-gated sodium channels. So if you open a ligand-gated sodium channel, is that going to depolarize or hyperpolarize those pacemaker cells? Think about that a second. So if you said depolarize, then you are correct. So Opening these ligand-gated sodium channels is going to depolarize the pacemaker cells. Now, this opening of these ligand-gated sodium channels, this does nothing to any of the other channels that we talked about before. It does nothing to the funny sodium channels, which are separate, does nothing to the voltage-gated calcium or the voltage-gated potassium. We're opening a new type of ion channel here. So what that is going to do, if you look at the bottommost figure here, because we have an extra influx of sodium other than just the funny sodium channels, this is going to get us to threshold much more quickly. So because we get to threshold more quickly, pacemaker potentials start happening more frequently. So we produce more frequent waves of depolarization, meaning that the heart is going to start beating faster because for every one of those pacemaker potentials, the heart should beat once. As the pacemaker potentials become more frequent, the heart will start beating faster and faster and faster. In the case of parasympathetic innervation, with acetylcholine being released by those parasympathetic postganglionic neurons, that is going to bind to muscarinic receptors on the SA node, and these muscarinic receptors will open potassium channels. If we open potassium channels, is that going to depolarize or hyperpolarize these pacemaker cells? Think about that. So if you said hyperpolarize, you are correct again. So the effect we see here on the frequency of pacemaker potentials is going to be just the opposite. With the potassium hyperpolarizing these pacemaker cells, that means it is going to take even longer for those funny sodium channels to get us up to threshold. We will eventually get to threshold, it is guaranteed, but the opening of these ligand-gated potassium channels is going to slow it down. So when you get parasympathetic activity, because you are slowing down and making the pacemaker potentials less frequent, your heart rate is going to go down as well. So you should recall that pacemaker potentials are guaranteed as long as the SA node is healthy. So any sympathetic or parasympathetic activity is only going to speed it up or slow it down. This is why we said that the heart has automaticity, because it is the pacemaker potential, which is guaranteed, that gets the heart to beat. All the autonomic nervous system can do is speed it up or slow it down. So let's look at a type of reflex here. So what you're looking at in this particular diagram is a type of reflex which is called a baroreceptor reflex. So one thing you may recall, if you don't recall it, that's fine, we're going to review it here. One thing you may recall is that we have receptors, sensory receptors, that detect changes in blood pressure. You see them here in the aorta, and you see it here in the carotid sinus. So the most common changes in cardiac output that we are going to see on an hour-to-hour basis within our bodies is in response to changes or fluctuations in our blood pressure. So what you're seeing here in green here is the afferent delivery of messages from these sensory receptors to the brain. So anytime we detect either a drop or a rise in blood pressure that are outside of our permissible limits, that afferent information is going to travel from these sensory receptors through our sensory neuron axons into the medulla and then up through the brainstem and up to the cerebral cortex if that is necessary. So that covers the afferent side of things, but the efferent side of things is going to be how do we modulate or change our cardiac output in order to bring the blood pressure back to where it's supposed to go. So changes to our cardiac output are made as the result of these sensory mechanisms that exist throughout the circulatory system. And it's not just for blood pressure. It can also be for things like how much oxygen is in the blood, how much carbon dioxide is in the blood, and even what is the pH of the blood, which will be things that we talk about in the next few chapters. So as I mentioned, baroreceptors are a type of sensory receptor that respond to changes in blood pressure. And they are located both in the aortic arch and in the carotid sinus. They measure blood pressure and then send afferent signals to the medulla in cases when the pressure in the blood gets too high or too low. A couple of other ways that we can get this afferent information to the brain. In one case, baroreceptors that exist in the right atrium measure how much blood is returning to the right atrium through the vena cava, and this is what's called venous return, the return of deoxygenated blood through the vena cava and back to the right atrium. The amount of venous return can fluctuate somewhat, and it is worth our time to measure that to keep track of how much blood is being returned in a given time frame. So, in cases in which venous return changes, or if blood is not getting back to the right atrium in a good way, this will stimulate sympathetic activity to increase cardiac output, and that is sometimes called the Bainbridge reflex. So, I also mentioned that in addition to pressure changes, we can also regulate our cardiac output in times in which the chemical composition of the blood changes, whether there's not enough oxygen or too much carbon dioxide, etc. We can change our cardiac output and a number of other things, including our breathing rate. So we will mostly talk about chemical composition affecting cardiovascular function when we start talking about respiration in Unit 5, so we won't worry about that for right now. The limbic system can also provide afferent information to the medulla to change cardiac output to coincide with a particular emotional state. Okay, so that pretty much up until this point covers how do we change our heart rate using the parasympathetic to lower it and the sympathetic to raise it. And you saw I guess I didn't cover it very well, so I'll go backwards here. So I covered the afferent side of things here, so you can see the afferent information go into the medulla, and then depending on whether we need to raise the heart rate to raise the cardiac output or lower the heart rate to lower the cardiac output, we can either take a parasympathetic pathway, you can see here, coming out through the vagus nerve and going to the SA and AV nodes. So that parasympathetic pathway would be utilized in cases in which the blood pressure is too high and we want to reduce the heart rate to lower cardiac output and lower the blood pressure. Or if the blood pressure is too low and we want to get the heart pumping to raise the pressure back up, we would instead want to utilize a sympathetic pathway that goes through a spinal nerve. And we can either raise the heart rate by influencing the SA node, pacemaker potentials, or something that we'll talk about here in just a second. You can see a separate pathway that leads into the ventricular myocardium, and that is going to be one of the many ways that we can change the stroke volume. So let's take a look at that. So like I said, in addition to changing the heart rate, we can also change the cardiac output by altering the stroke volume. But the stroke volume is a little bit more complicated, and there are three major ways that we can either change the end diastolic volume or the end systolic volume. Don't forget, the stroke volume is just the difference between those two figures. The first way we can influence it is through what is called preload. Preload is essentially the same thing as your end diastolic volume. It refers to the volume of blood that is in the ventricles prior to systole, and it can be changed due to a change in venous return. So basically, if you have an increased flow of venous blood returning to the right atrium, that is naturally going to lead to an extra big end diastolic volume. Contractility refers to the strength of each particular ventricular contraction. So basically, if we get an extra strong and extra big squeeze through the ventricular myocardium, we can push an extra big volume of blood out into the systemic circuit. So this can be strengthened by the sympathetic division to increase your stroke volume while decreasing the end systolic volume. That's just a natural compromise. If you increase your stroke volume, you do that at the consequence of decreasing your end systolic volume. And then your afterload actually refers to the arteries themselves. So this actually refers to the resistance to blood flow in the arteries, which will determine how hard the ventricles have to work to compensate for that. So basically, this is another multifactorial thing, but for us, we can kind of simplify it and consider afterload to be a balance between vasodilation and vasoconstriction. Basically, if this is the opening of an artery, if we dilate an artery, we decrease the afterload. We reduce the resistance to blood flow, so the ventricle is not going to have to work quite as hard to get that blood to flow through a very wide open vessel. But if we vasoconstrict that artery, we increase the resistance to blood flow, and the ventricles are going to have to pump extra hard in order to get that blood to flow through a very narrow vessel. So let's talk about preload first. The first thing we'll say about preload is really fairly simple. If there is more blood in the left ventricle at the end of diastole, then the stroke volume is going to naturally be greater because of the mathematical relationship at play here. So think of it like this. If our typical end diastolic volume is 120, and if our ejection fraction is roughly 2/3, then your stroke volume is going to be 2/3 of whatever your end diastolic volume is. So 2/3 of 120 is 80, right? So that would be your stroke volume. But let's say you have an increased preload. You have increased venous return to the atria, meaning that instead of, say, 120 milliliters as your end diastolic volume, maybe it's 150. So 150, 2/3 times that is going to be 100. So if you increase your end diastolic volume, your stroke volume is naturally going to go up just because of that relationship between the ejection fraction and the end diastolic volume and the stroke volume. So because the ejection fraction is always going to be roughly 60 to 70%, an increase in end diastolic volume will naturally produce an increase in stroke volume. Additionally, in cases where you do have an increased end diastolic volume, you are going to produce a greater amount of stretching force on the ventricular myocardium. So picture a kind of latex balloon, just a regular old rubber balloon. Say you get a water hose and you start filling up this balloon. So as the balloon starts to fill up, it stretches and stretches and stretches. What do you think is going to happen to the wall of that balloon as the balloon fills up and up and up? We stretch the wall of that balloon up and put a great amount of tension on it. So do not forget that the ventricles are chambers that can hold a certain volume of fluid, blood. It's not unlike a balloon. But the wall of this balloon is cardiac muscle. So when you increase the amount of volume that is occupying a ventricle, you are stretching the sarcomeres of that ventricular myocardium out. And when you stretch them out like that, when they eventually contract, they're going to contract with an extra amount of force. And this is described by what is called the Frank-Starling law. So if you look here, in cases at the bottom here where the sarcomere in the cardiac muscle fibers are not stretched out at all, you're not really going to produce a whole lot of tension. So you can see A there corresponds to a very small amount of tension once contraction occurs. But as you increase the end diastolic volume and you really start to stretch that sarcomere out, you greatly increase the potential for how much tension can those cardiac muscle fibers generate. And as they generate more force, they're going to produce a much greater stroke volume, even greater than what we described with just that mathematical relationship. So here, a greater end diastolic volume will actually cause the myocardium to stretch on its own, and this is called intrinsic control of contraction strength. Intrinsic meaning this is something that the heart itself actually deals with. No influence from the outside. So now we can talk about what is called extrinsic control of contraction strength, and predictably, this level of control comes from the autonomic nervous system. And specifically here, we are not talking about a mathematical relationship. We're not talking about changing the stroke volume just because there's more blood there. We're actually talking about getting the cardiac muscle to contract with an extra amount of force, again, coming from an extrinsic control center. So this diagram that you're looking at here, I don't want to spend too much time on it, but basically you're seeing a comparison in how stretched do you have to get a sarcomere to get a certain amount of tension. So for skeletal muscle, it does not really take a whole lot of stretching force in order to get yourself to tetanus, to maximum tension. If you look at cardiac muscle without epinephrine, without a sympathetic regulator, this is the far right figure here, the kind of dark orange one. So cardiac muscle without any sympathetic stimulation has to really work itself hard. It has to really stretch itself out in order to get itself to maximum tension. However, with epinephrine, with a sympathetic stimulant, we can actually get cardiac muscle to behave much more similarly to skeletal muscle. So it starts working more efficiently, and as we said, we can get it to work harder and to produce a stronger stroke volume and a greater cardiac output. So basically the way this works, so cardiac muscle itself has beta adrenergic receptors like we've discussed before. So any epinephrine or norepinephrine coming from either the blood or from postganglionic sympathetic fibers, those regulators will bind to these adrenergic receptors. And there's a lot going on in this second messenger cascade that you see here. Don't worry too much about it. Basically, the idea is that we can actually get the sarcoplasmic reticulum to release an extra amount of calcium, meaning that we can get more sarcomeres engaged in a power stroke, so we can get a stronger muscle contraction to occur. That's all you really have to remember about that. And then the last thing for us to discuss here is the concept of afterload. The idea that this total peripheral resistance, this resistance to blood flow in the arteries, can actually influence how hard the ventricles have to work. So do not forget, in order for the ventricles to pump blood out into the arteries, the pressure in the ventricle has to be higher than the pressure in the arteries, because as we've said a million times already, blood will flow from high pressure to low pressure. So the idea here is that if you have your arteries and they vasoconstrict, that drives their pressure up. So if you want the ventricles to pump blood through there, their pressure has to be even higher. So the higher the arterial pressure, with nothing else changing, the lower the stroke volume is going to be, because your stroke volume is going to be proportional to the difference in pressures between the ventricle and the arteries. So if you're trying to get my hands oriented here with the camera, if your ventricular pressure is here and your arterial pressure is here, that difference between the two determines your stroke volume. So if the arterial pressure comes up, there's no longer as big a difference, so your stroke volume is going to suffer. So the way you remedy this is you want your ventricles to work harder to get their pressure back up so that they can maintain a steady stroke volume. So like I was saying, a healthy heart will actually compensate for a momentary increase in blood pressure and arterial resistance by increasing ventricular contractility and increasing your heart rate. Both of them will increase your cardiac output, increase your blood pressure, and then get the blood to flow through. So basically the idea here is that in order to overcome increased arterial pressure, the heart has to work a little bit harder to get the blood to flow through. That's for a healthy heart, but of course you're aware that high blood pressure is an issue for a lot of people, so we kind of have to walk a balance in reducing the blood pressure so that the heart itself doesn't have to work quite as hard to get the blood to circulate. So let's review what we've talked about so far. The most important thing to start off with is cardiac output, which is equal to stroke volume times heart rate. Let's review how the autonomic nervous system can influence the cardiac output through both the stroke volume and the heart rate. Number one, sympathetic or parasympathetic stimulation of the pacemaker regions produces what is called a chronotropic effect, meaning a timing effect on the heart rate. The sympathetic division can increase your heart rate to increase your cardiac output. Your parasympathetic division can decrease your heart rate to decrease your cardiac output, assuming that the stroke volume has not changed. Secondly, sympathetic stimulation of cardiac muscle itself, not pacemaker, but cardiac muscle itself, that surrounds the atria and the ventricles, produces what is called an inotropic effect on the contractility of the cardiac muscle. Basically, we get the cardiac muscle to contract with extra strength, either because of the stretching forces from the Frank-Starling law or because of the extra availability of calcium in the sarcoplasms. So the idea here is that we increase contractility, we get the heart to pump with extra force, we generate a greater pressure difference between the ventricles and the arteries, and we can get the blood to flow the way it is supposed to. So this diagram is kind of a good study guide for you. It lays out how to calculate cardiac output, cardiac rate, which is your heart rate, stroke volume, and then you can see tied into each of those all the different things that can influence them. So one thing that is not provided here, which I think is an important piece of context, if you see a dotted line, that means that this, in this case parasympathetic nerves, has a negative influence on it, meaning if you see a dotted line pointed towards the heart rate, that means the parasympathetic nerves will decrease your heart rate. A solid line means it will increase it. So sympathetic nerves increase your heart rate, parasympathetic nerves decrease your heart rate. Total peripheral resistance, you see a dotted line here, an increase in total peripheral resistance and arterial pressure will decrease your stroke volume. An increase in diastolic volume will increase your stroke volume because of that mathematical relationship that we talked about, but also because of the stretching forces that you get from the Frank-Starling law. So make sure that you look over this very carefully. If you need me to make a kind of separate review video about it, just let me know. I'd be happy to do it. And that's going to do it for Chapter 19. So we've talked about an awful lot of things. We've talked about the direction of blood flow. We've talked about pressure differences and how that dictates the direction of blood flow. We've talked about cardiac muscle fibers. We've talked about electrical stimulation of the heart. We've talked about EKGs. We've talked about cardiac cycles. And now we've talked about how your nervous system is capable of regulating the function of your heart to meet with certain homeostatic and metabolic demands. So our last chapter of this unit is going to be Chapter 20, in which case we will take a closer look at the vascular itself, meaning arteries, veins, arterioles, capillaries, and venules. We'll talk about blood pressure measurements, and all sorts of other sorts of fun things that come with the territory. So I will go ahead and sign off for now, and I will see you next time. Bye-bye.